Hello and good evening, good morning, good afternoon, everyone. Thank you for joining us for this video. And today with us, we have Professor Andrew Rees from Swansea University in the UK. In this video, you're going to learn about the structure of an engineering program in the UK, about how the program is structured, about the future job prospects in this field. And we are excited to have you here with us, Professor Rees.
Oh, thank you much, Devish, and thank you for the kind introduction to help you. Say it's something that we're really happy to do. We're based in Swansea in the UK, but yeah, say very happy to contribute to this today.
Thank you so much. So before we go ahead, let me introduce Professor Rees. Dr. Andrew Rees is an associate professor and head of mechanical engineering at the Faculty of Science and Engineering, Swansea University in the UK. The Department of Mechanical Engineering at Swansea has over 700 students and is ranked at 9th in the UK for its research excellence. In addition, the department is also impressively ranked within the top 200 departments in the world within the QS ranking league table. Dr. Rees started his engineering career within the automotive engineering before making the transition to academia. Therefore, he brings his industrial experience into both his teaching and research. The focus of Dr. Rees's PhD was microelectrical discharge machining for application within the production of micro-injection molding and micro-components manufacture. With regards to his research, Dr. Rees is regarded as a global expert within the field of advanced manufacturing engineering. He has published over 20 peer-reviewed journal papers and authored 4 books. Dr. Rees is also a chartered engineer and a senior fellow of the Higher Education Academy. It's such a great pleasure to have you here with us today. And maybe we can get going. So let me ask you my first question. And that is, what is the engineering, what is mechanical engineering, and how is the engineering program structured across the years?
Okay. Well, thanks again for the lovely introduction, and well done on some of the terminology. Okay. So I think the easiest thing, the way for me to do this is if I share my screen now. Yes. I've got a little presentation which will maybe bring some clarity to the audience.
Absolutely. Perfect.
Okay, so as you said, so I'm Andrew Rees from Swansea University in the UK, and I'm head of mechanical engineering. Sort of before I go too much into the structure of what a major, as you term it, or we call it degree, is in mechanical engineering. Basically, better start off by introducing you to exactly what mechanical engineering is, okay? Because it's quite a broad term, and it's surprising what people don't really understand how broad it is and the different places it's applied. So my definition, okay? So this isn't in the Oxford Dictionary or anything. It's just what Andrew from Swansea says. It takes the principles from physics and maths and uses them to create something tangible. Okay, so that's a bit of a broad sweeping statement there. So maybe I'll try and give this some context, okay, by maybe giving you some case studies to understand it. So for example, so say this is a plane, okay, so this is the Airbus A380, and so this is the biggest air passenger aeroplane on the market today, okay. But when an aeroplane comes into land, okay, so you've got this massive weight, obviously, okay, of the plane going to hit the runway, and all the fuel in a plane is stored in its wings, okay. So what we don't want is that when that plane hits the runway, the wings, because of the weight that's in them, touch the runway, okay. That's going to be a bad day in the office for someone, okay. So typically what mechanical engineers do, we look at some principles, again, so some scientific principles. For example, mechanics and the deformation of materials is one, okay, so that we know that we can calculate what weight is within the wings from the materials. We know what sort of material properties there. And what we can actually do, we can actually predict how much those wings are going to deflect. when that plane comes into land. Okay, so this is mechanical engineering. Okay, so this is one of the thousands or maybe even more applications of where we can apply it. Okay, so I'll give you a broad taste of it as well. So another one is generation of electricity. Okay, so in the UK especially, okay, we have lots of coal-fueled power stations, and essentially all we're doing when we're using a power station, okay, is we're transferring energy from one form into another. So typically what we're doing with this, we use thermodynamics, and we are using the volume increase you get. So when you heat water, it creates steam, and what that steam does, it gives you a massive increase in volume. We then push this through a turbine, and we convert in essentially motion into power. But in all these fundamental calculations, what temperature the water needs to go to, what thermodynamic cycle, again, all these calculations are done through mechanical engineering. Probably a bit more exciting one, okay? So Formula One, okay? I think this is probably the best example where you see lots of fields of mechanical engineering working together, okay? So typically, if you look at the design of a Formula One car, okay, one of the big sort of attributes of this is, so we've got spoilers, okay? So we've got at the front, the back. So we call this the aerodynamic pack. And basically, what we are trying to do with those, we're trying to optimize the performance of the car when it brakes and when it accelerates, okay? And what we're actually doing by introducing an aero pack on a car, we're actually changing the fluid profile, okay? So this is called what we call fluid dynamics. So essentially what we're doing, we can fluid, so air is a fluid, okay? It's not always water, it can be oil, it can be anything. It comes in two forms, to what we either call laminar or turbulent, and depending on what function we're doing, we'll want either one of those. So that's what our aero pack, okay, gives us downforce and things like that. But essentially what we're doing during all those stages, we're engineering the preferred dynamic form that we want, okay? So that's a good one. So it's much wider as well. Okay, so I'll give you some examples there, but manufacturing engineering, it covers how, say it's run in my university, the core of it is design, okay? So you design every year of your study, and then this is complemented then by manufacturing is a really big part of mechanical engineering. So it's how do we mass produce components, and this could be through a range of different technologies. So typically additive layer manufacture, robotics is a big part of it, polymer processing, control systems. So one thing about mechanical engineering is quite broad, okay? It's not all about hard mechanics. You learn about electrics, electronics, materials is a big part of what we do. So say we need to know how materials are going to behave, how we process them, things like that. Project management, okay, big part of engineering. Unfortunately we lose a lot of our graduates to project management positions, so they don't always progress to say technical sort of positions. Sometimes it's project management because again, every year your degree you're exposed to this because we have to work in teams a lot in engineering. So project management, big part of it. And also things like critical thinking. Okay, you have to have a very critical mindset to be an engineer. You need to question things, you need to evaluate things, and from that create solutions to it. Okay.
Perfect. So that takes care of what is mechanical engineering. Would you explain a little bit about how would the academic structure or the curriculum structure or the program degree structure be at a university in the US, or more specifically at Swansea?
Yeah. Okay. So with our academic route, we call it then. So we say in mechanical engineering in the UK, most universities we usually run 4 different qualifications. So we run what we call sometimes a foundation degree, which is basically a 1-year degree where typically if you haven't got the entry profile that we think that you need to come into a bachelor degree, you can have a 1-year foundation degree. So it's sort of an upskilling year, just in case you didn't choose the right options at school. For example, if you didn't do maths or science, this is the year that we do to upskill you to make sure that you could cope on our other degrees. So say 2 other degrees we do. We do what we call a BEng, which is a Bachelor of Engineering, and this is a 3-year degree. We also do what we call an MEng, which is a Masters of Engineering, which is a 4-year degree. And finally, we do the last one, which is an MSc, so it's a Master of Science, and that is a 1-year degree. And you usually do that as a sort of postgraduate qualification if you want. How most universities, especially top-tier universities like ours in the UK run, is that what we do with the degree structure is that we allow you to, usually between years 2 and 3, to have either an industrial placement year or have a year abroad. Okay, so this is we found this this structure works really well. I think it's really good that a lot of universities in the UK, they run this structure because it gives you context of what you're learning in the classroom, especially the year in industry. It's fantastic for you, okay? And what we found, especially at Swansea, is that when you guys come back from your year in industry, that you actually perform much, much better in your final year because you've seen where you're going to use all this theory in practice. So that's the model that we follow. So essentially, you say there are a few different routes, but sort of the main ones I'd say are the BEng and the MEng.
Okay, perfect. And what could be some concentrations within engineering? What are certain within mechanical engineering? Are there various branches that we look at?
So, say with mechanical engineering, it's really around manufacturing is a big part of it now, and this is really changing of late. It's really helping now. Materials, like you say, programming now is becoming very popular. So things that we've got Python being taught now within our degree systems. So yeah, so they're the kind of major concentrations really within the degree, or what forms the degree.
All right. Okay. So shall we move on to the next question?
Yeah, certainly.
That is about what kind of students will do well in engineering. What are certain skills that students must work upon to succeed in this degree?
Okay, right. That's a really good question. I like this question. Okay, so okay, I think to be an engineer, you need to be they're definitely what we found. Our successful students, they've all got similar traits. Okay, I probably think the biggest one is you have to have a strong work ethic. Mechanical engineering, like other degrees, especially in the area of science, okay, it's very intense degree. Entry standards are high, and they have to be because the technical content is difficult. Okay, so, but generally, if you've got a really good work ethic, you know that's not an issue for you. So that for me, that's a key one probably. You've got to really, you know, you've got to want to do this. You've got to be hungry, and if you've got that you know that's half the battle. You know, engineering, it is, you know, it's called a science of engineering, so it is a science. So, you know, as default, you should really be interested in science and maths because it's at the core of what we do. It's, you know, there's very little engineering that isn't some sort of science or maths based task. Okay, so you know that's, you know, I know, you know, on my personal journey, I loved maths in school, right? I absolutely, and I still do, and that was probably one of the reasons why I decided to become a mechanical engineer. Logical mindset really helps. Okay, you know, if you're a logical person when it comes to working out problems, that really helps. You've got to be very disciplined. And that comes into a good eye for detail, okay? You know, a lot of what we do in engineering, if we get it wrong, there can be, dire consequences. Okay, and that's why it's a highly paid profession in the UK. Okay, it's it is seen as a profession. It's not a job. Okay, being an engineer is a profession. And this eye for detail is really important, because say if we get things wrong, we underpin so much of society. You think of, what you've done today. So you've probably come to school or something in a car. That's all been designed by engineers. The road, okay, the mechanical analysis is a mechanical engineer there somewhere. The building you're in, there's mechanical analysis in there, okay? So we do underpin society, essentially, okay? So that's why we have to have this good eye for detail, because if we get it wrong, you say there could be terrible consequences. You've got to be a team player, okay? And again, this is, I think, a really good characteristics you've got to have with engineering problems or engineering tasks. A lot of them are huge, okay? So, my experience, I started my career in the automotive industry, okay? You'd work on teams with 100 engineers, and if you're not a team player, that isn't going to work. It's not about promoting Andrew Rees, it's about how you galvanise a team, work within the team, and all work towards a common cause, okay? And it's really vibrant, I love it, okay? The team dynamics are probably one of the things I really enjoy being a mechanical engineer. You've also got to be good at dealing with ambiguity, okay? So what I mean by that is that a lot of the time in engineering, you don't get things like full data sets, okay? So you have to make assumptions a lot. They're always calculated, okay? But if you're the type of person, it either has to be black or white. Engineering isn't for you, okay? You've got to think outside the box a bit. And, we have to make calculated guesses, essentially, sometimes. But they'd always be verified after, okay? So dealing with ambiguity is a big one. And you must be passionate, this is my last one, about forever learning. I've been involved with engineering now for over 25 years, okay? So I started quite young. And my biggest driver is that every day I learn something in engineering, okay? Through my research, through my teaching, through my industrial engagement, every day I learn something. And that's what drives me in my career. And in engineering, if you haven't got this desire to learn every day, you get left behind, and you get left behind very quickly, and you then become displaced because you're not relevant in your field anymore. So, it's a really fast-moving, paced profession, and that's what I love about it, okay? The technology enhancement, it's always changing. You could, go away for 1 year looking at a field, come back the next, you don't know what's going on, and that's fantastic for our profession. Okay?
Fantastic. That's wonderful. Yeah, I mean, curiosity and a passion for learning new things, absolutely, very, very important. But all the other points, of course, I think having a logical mind, strong work ethics, and of course, having an interest in science and maths, very important for being an engineer. A little trivia here, I also did engineering. I studied bioinformatics at college. Bioinformatics is at it's the merger of biotechnology and computer science. So yeah, okay. So moving on, let's move on to the next point, which is what do you see your students typically do upon graduating? What kind of jobs do they get into, or what kind of postgraduate courses do they get into usually?
Okay, right. So again, I'm liking these questions. Okay, so right. So I think one of the a really strong aspect of, especially mechanical engineering, okay, is that it's very, very broad in terms of where your career can take you, okay? I'm going to use myself as an example here now, okay? So, say I've been a mechanical engineer for 25 years. I've worked in the automotive industry, okay? I used to work for a big multinational company called Valeo Climate Control, and I used to manufacture heating and air conditioning units for the automotive industry, okay? I've worked for Johnson & Johnson, Okay, so you might think, good God, Johnson & Johnson, that's medical stuff, yeah? But I used to work as in a manufacturing site developing drug diagnostics kit that would typically they'd be used for detecting HIV, okay? But I'm a mechanical engineer, but you see, it's really broad. I've had a job working in food industry, okay, which was a really strange one, but I used to design ovens, okay, because a lot of the thermodynamic, a lot of the mechanical elements of it is mechanical engineering. And what, you know, that job I really took because it really shows how diverse mechanical engineering could be, you know. I had to go on a baking course, okay, to learn how to make bread, but it was delving into chemistry, biology. It was fantastic, okay. It's really, really broad field. Then I came into academia, and I worked in my PhD's in micro nano manufacturing, essentially. And to say the focus of my PhD was I was developing micro holes, we call it, to use in diesel injection nozzles, okay. So, and what that was doing, if we could produce smaller holes in the injector nozzles, it meant we were releasing less emissions. So again, that's, you know, shows how broad it is. You know, with our graduates in Swansea, okay, we've got Tata Steel, okay, which I'm sure you all really know well in India, okay, but I'm literally looking out my window now and I can see Tata Steel in Port Talbot, which is really close to us. So, you know, a lot of our graduates end up there. Rolls-Royce, okay, not just the cars, but also in the engine designs for aeroplanes. Airbus, so a lot of our students go to Airbus every year, and BAE Systems, so they're both, although they are aerospace companies, you know, as a mechanical engineer, it's really easy. You don't have to do an aeronautical degree to work in either of those. A lot of it is, you know, fundamentally mechanical engineering. Aston Martin, okay, they're one of our partners here in Swansea, so we do lots of research for them. Arup, so they're actually a civil engineering company. But again, civil engineering, you need mechanical analysis in there. So I know last year, the 8 graduates they took from us, so that was good. And just one is, I'll give you the last one now. This is a company called Vendico, and they're a small company based in close to Swansea. And again, I just wanted to demonstrate the breadth of careers you could have. So we've got 2 graduates in there now, and I've got a PhD student working with them. And basically, this company develop systems to analyze air quality. That's going to be used on in the global market. So essentially, they make these little boxes full of sensors, and they're measuring things like ozone, stuff like that. And they're in city centres to monitor the pollution levels and give continuous feedback. So that, for example, in London, sometimes they have car-free zones. And that's because, emissions are too high. And again, but a lot of that instrumentation that's developed, it's multi-teamed, but, you know, the core of it is mechanical engineering. So, you know, looking at the big data analysis, it's you know, we've got mechanical engineers working on that. So it really shows the sort of breadth of careers you could have through studying engineering.
Wow, that's wonderful. And I mean, it's really amazing to hear. Being an engineer, you went ahead and you had to learn baking. Same way, there's so many interdisciplinary things happening across different sort of companies, different organizations, and engineering is sort of one theme which holds all the manufacturing or all the sort of product designs at the core of it. That I think that's engineering is. And then you take something from, let's say, from a different field, from just like you said, baking, or you take something from the other field and merge all of them together to sort of create new innovative things. Wonderful. So that brings me to my next question. That is, where do you see this major going in the next 5 to 10 years? What are some new future trends or some innovations that you see coming into this?
Okay. Right. So, okay. So future trends. So literally, this is our campus in Swansea here, and all of these different buildings here. So we see we're right on the beach. Okay. So it's a beautiful place to work and study. But each of these buildings here are what we call research centres. Okay. So each of them are working on different themes. So I was going to give you a few examples of what we're seeing as trends. So I think the big one is engineering now is getting very well. It's adopting a multidisciplined approach, okay. And it's interesting. Dare I should say your background, and this is a really good example of where sort of biotechnology and computer science come together, and we're seeing that a lot now in engineering. Even in our college, we've always had a strong background in materials, mechanical engineering, aerospace, but medical engineering now is a huge growth theme. And what we're finding is that now where we teach fluid dynamics, where before we'd concentrate on oil and water, now we're talking about blood. Because if we put too much shear stress in blood, if we're designing a heart pump or anything like that, we damage the blood. So it's becoming much more multidisciplined. I think that the biggest one for us now is computer science and engineering are really merging. So our computer science department now in Swansea has actually moved onto our engineering campus, because the merger now is not just virtual, it's physical, because there's so much crossover. A lot of, say, manufacturing engineering now is computer-based analysis. It's about simulating processes, simulating material responses. So there's a lot of synergy there, and also with business as well. We are seeing now we're getting more interest in potential students asking whether they could do courses that are a bit of a mixture of business and engineering, so that way you get a bit of a better balance profile there, where you get the entrepreneur stuff from the business, and you get sort of the hard engineering then from your engineering course. So I think that's all healthy. Other ways, I think we are seeing now a massive digital transformation. In my field of manufacturing especially. So now, for example, we create what we call digital twins. And what this means is that where before we'd have a machine that was, say, producing, car bumpers. Before that would just be a physical machine. What we now create is what we call a digital twin. So we replicate the full process in a simulation package to help optimize the process. So digital twin is a big thing. Additive manufacture. Massive, we haven't got loads of materials now, so we've got to look at cleverer ways to do it. And I think this has all been driven by what we call mass customization. Okay, so as consumers, okay, we're really fussy now. So whereas before, say if you wanted to buy a car or something, you could only buy a white one. That wasn't that long ago. Okay, now you want a white one with a black roof, with orange alloys, left-hand drive, and a fluffy dice on the mirror. So our manufacturing processes have had to adopt and become really agile to meet what we call this mass customization trend. Okay, and that's not going away. I think that's good. So that is really starting to shape the content of curriculum and engineering moving forward. And finally, I think there's now, especially we've seen it in the UK, okay, there's much more emphasis now on sustainability in terms of environmental sustainability. So we've got a big centre in Swansea looking at alternative energy supply. So now you literally, if you build a factory in the UK, you can't. It has to be almost off grid. So it has to have photovoltaics, biomass, heating systems, things like this. So again, that's a big growth. Green manufacturing is big as well. So whereas traditionally, when you optimize a manufacturing process, it was all about mass production. Now that's changed. You optimize a manufacturing process now to minimize energy usage. So green manufacturing is a big growth field. And finally, recycling. As engineers, we play the biggest part in the supply chain of determining what materials, and we have to be more creative now in what we're looking at, and think about post life as well. So that I say that is literally happening now within our degree system, where students are actually getting assessed in design projects on thinking about sort of post-use or recycling of materials.
That's fantastic. Wonderful. Really, really, all these things. It's fun to imagine how this would change the world in the coming few years, right? I mean, the phrase customization in itself, it sounds like an oxymoron. Like, how can that be? But yes, absolutely. You sort of explain that in a beautiful way. Like you're building that car, and then you want a white roof on a black car, and then you want so many of those cars. That's a customized car for sure. So, but I want to know what I mean. I didn't really catch what digital twin is, or maybe can you give me another example of what digital twin is?
Yes, yeah. So, for example, there's a manufacturing process called injection molding. Okay, so it's used for say the back of your PC monitor. There is a plastic part that's replicated. Well, it's produced through a process called injection molding. So what our research is looking at now is developing. So obviously it's made on a machine, and what we've developed a CAD model of the machine. And we look at all the various elements of how the material is transported, how the polymer is injected into the material, what happens if we change the material, and we produce this digitally. So it's on a computer software. The package we use is called MoldFlow, and so what you want to be able to do is really optimize it before it becomes a physical process. So you can say, right, okay, if I'm going to change from polypropylene to ABS, actually what does that look like? And you might find, oh my gosh, hang on, we actually need to use 5% more material or 20% more energy to produce this, but we can do it all digitally before physically having to try it on the machine. So that's a massive growing trend in
Wow.
In engineering.
That's wonderful. So that means it's also got a lot to do with the material engineering, right? Like, uh,
It's everything, yeah. Yeah, it's materials, it's fluid dynamics, it's heat
oh yeah,
transfer. So it's multi-physics modeling basically.
right.
So
Wonderful.
all put into one package.
Fantastic. Well, thank you so much for sharing so much information with us. We're almost coming towards the end of this presentation. And before closing, I would like to ask you one final question. That is, if you have any piece of advice for the high school students who are watching this video.
Whoa. Right, I get asked this quite a bit, okay? And if I'm thinking about my career and okay, so I've talked about it. The big one is you've got to have a good work ethic, okay, and take responsibility for your learning experience. But please don't leave mum and dad nag you all the time, okay? You should be wanting to do it. But I think the biggest, when I've reflected on, say, where my career's gone and where I felt it slowed down, where it speeded up, and it speeded up when I've gone outside my comfort zone, okay? So if my feeling is, as you grow as a person when you get outside your comfort zone, say you might not like presenting, okay, but you present in front of a public audience. When you get there, you think, why have I done this? Okay, why have I put myself in this? But this is how you grow, okay, and it's about if you stay in status quo, you're very risk adverse, okay, you're not, you're going to have a good life, but I don't think it's something that's reaching your full potential. So that's my thing. Don't be afraid to get outside your comfort zone, because you always learn something from it. You might have a disaster, but you never make the same mistake again. And remember, he who has never made a mistake has never done any work. Okay, that's an important one. So,
Wow.
so don't be afraid of that.
Fantastic. That's really a great piece of advice. Not just the students, but adults like us can also use that. So wonderful. Thank you for sharing all that information, Dr. Rees. It was really a pleasure to have this conversation with you today. Thank you so much for your time this morning.
You're very welcome. It's lovely to meet you all, and good luck with your careers.
Thank you so much. Have a great day.